Hi guys, welcome back to another episode of Pollys Introduction to Computer Networks. Alright, so good morning. If you're here, just say hi. Alright, and let's check out the announcements today. So we have the regular announcements, the links to the video channel. Oh, hi, Ouyang, Sylvain. Oh, you guys are early. Yeah. So you'll see also that Polly is an early person. Okay. Polly hasn't made the change, and Polly promised herself to make the change to be a morning person than being a night owl. Okay. Hi, Jeremy, Justin, Zhenyu, and Kekori. Okay. Yeah. I hope that I pronounced that name right. You know what? For Thursday, we don't usually have new things we want to talk about, but today we do. Check out the announcement number 3. Yeah, this is the 3rd week, guys. You've survived 2 weeks. Congratulations. The class is finally final. Polly is just, much more relieved, okay, when the class is settled. So she can generate this Google spreadsheet that records the marks of your assignments and participations throughout the semester. So this is ready. If you click into the link, you should see a Google spreadsheet like this. Okay. Inside you will find 3 worksheets. Okay, so this one is the PA worksheet. You see that you guys have all completed PA1 and received a full score. And this week we have the PA2 doing. And when Polly is done grading all the PAs, you will see the numbers showing up here. Okay. The second worksheet is to record the quizzes. Q1, Q2, I have to say are more or less trivial. But Q3, you guys did very well, and we had good interaction going on there. So all of you received this extra bonus. And for those answers receiving extra bonus, I would use highlights. Okay. And so you see from last week, Q4 and Q5, some of you guys' answers are more thoughtful, sometimes faster. Okay. So for straightforward questions, I was looking forward to faster solutions. But for more open-ended questions or open-ended quizzes, I was looking for more thoughtful ideas. And so you see that in some quizzes, faster teams earned extra bonus. And in some other quizzes, more thoughtful teams earn the bonus. Q6, we just gave this one out yesterday, and I see 4 of the teams have complete. Hi, Miguel. Tao, Zach, and G. I see that 4 teams have already uploaded their solution. You know what? Polly is gonna, assign the bonus by comparing. Okay, relatively speaking, who are more thoughtful and which teams are more thoughtful than the others. So for Q6, quiz 6, I'm gonna wait until all the teams finish submitting their solutions and decide who will receive, which teams will receive the bonus. Okay, so thus you get a rough idea how your quiz is going to be tracked. And here the 3rd worksheet is participation. You see that we have the participation marks for week 1. Whoopsie. Week 1, which is right here. Oh, okay. Week 1 right here. Week 2, and you see 4 categories where you receive the participation marks. This is the chat, YouTube chat category. This is the score category, and then there's office hour category, and then the email category. Okay. And so far what I see is that you guys are extremely active on the score, which is good. For online course, this is just perfect. And by the way, you will also see that Polly will stop at 5 points per week. Oopsie. Poly will stop at 5 points per week. All right. So there's a cap too. So it's not like you need to be. It's not like you can be very active the first week and then you earn all the points for participation. So I was looking for continuous, consistent output. All right, great. And I see Zoe and Maria. So hey, I hope it's clear how you guys are gonna be graded. Exams, it's actually coming up in 3 weeks. You will see as well. All right, back to the topics. Yesterday, we introduced 3 metrics we use to evaluate the performance of a network. Delay is actually quite complex. You see there are 4 components. Some are easier computed, some are harder. There are 2 more. Loss. Yeah, this is critical, right? When buffer gets full, packet get dropped, so we have loss. Okay. Another one is called throughput. Now this one is a new. Okay, but let's start from the easier one. Loss. The video is very short, 1 minute. Packet loss is a lot more straightforward. You see, it's because the queue is finite in capacity. So in case a packet arrives when the queue there in the router is already full. So you see this full packet here, will need to be dropped. That's why we see packet losses. Now, what we haven't discussed is this, the lost packets. To some application, it's actually okay to have packet losses. If it happened, let it happen. So we will not try to retransmit the packet at all. But in some cases, for some applications, users are expecting the messages arrive fully intact. Then we might need to retransmit. Now, as to which entity in the internet to try to do the retransmission, it's really up to the design. So in some cases, we might see the previous routers doing the retransmission. But in most of the cases, we see the original source, the source end system is doing the retransmission. All right, so loss, again, straightforward. And the only way to address loss is to retransmit. Okay, well, actually, those who are interested in multimedia content, sending multimedia content over the internet, you might learn also there's another way, which is called encoding. So you actually send slightly more bits in the original content. So at the receiver end, you might be able to recover the lost bits or lost content from these extra bits. Okay. All right, and next one, throughput. I have to say that the unit of throughput is number of bits per time unit. Okay, that sounds like the transmission rate of a link, isn't it? The number of bits we can send per second. The unit for throughput is the same, but transmission rate for a link is just transmission to pass data through one physical link. But throughput talks about passing data from the data source to the data end, the entire pass, not just a link. Okay, so this is throughput. Throughput is the third metric, and it measures this thing, the rate of transmitting data all the way from the sender to the receiver, from one end to the other end, and the speed of data is going through the entire channel, entire pipeline. Now, there are 2 ways of quantifying throughput. One is called the instantaneous throughput, the other average throughput. Now the units are both bits per second. Okay. But instantaneous throughput is more that you're measuring the throughput at a particular point in time. You will see that if you measure instantaneous throughput, it will fluctuate depending on the situation of the channel between the source and destination. But if you observe over a longer period of time, then you see that the average throughput is more or less stable. Okay. So the throughput here we're talking about and discussed throughout the rest of the slides will be more the steady state behavior, the stable average throughput, just to clarify. Now let me elaborate the example a little bit more. This is the sender, this is the receiver. The sender is essentially a file server hosting big files here. Let's say the file of f bits is being sent over to the client requesting the file. And so we're talking about just the file download, okay, not the request part. And connecting the server and the client, we have one link, one switch, and another link. So it's a two-hop network. And the link capacity for the link directly adjacent to the server is RS, and S here indicates it's the link to the server. And this guy here has the link capacity of RC, and C indicates this is the link rate for the link connecting to the client. Now, let's consider, okay, such a data pipeline as a fluid pipeline, water pipeline. Then you see, I'm drawing, okay, the pipeline's width, the diameter, based on the link capacity, RS. So RC here, let's assume it's larger, then you see a bigger pipe versus RS, smaller pipe. And you can also think about the server here being a what? Okay, a water tank, dumping fluid into the entire pipeline here. Now, it might be a little bit easier for you to imagine, right? What is going to be the pipeline's throughput if you consider how the fluids will be arriving at the receiver effectively? Would it be RC or RS? Well, it's probably not that hard, isn't it? Because the intuition tells you that, hey, this guy here, RS being smaller, will limit the amount of fluid that can travel through. Okay, even though RC is bigger, yeah, the amount of water that will go through here effectively to the receiver is still RS. If it's the other way around, RS being larger than RC, yeah, there could be a lot more water coming in, okay, overall carrying RS throughput, but this guy here being thinner is going to limit the rate of the fluids travel through. So in the end, at the receiver, okay, RC is going to be the throughput. And this guy here and this guy here, the link on the end-to-end path with the smallest bandwidth is going to constrain the eventual throughput. Okay, so throughput here oftentimes is being called the end-to-end throughput to indicate that it's the rate of data being sent from the source, one end, to receiver, the other end. Well, after drawing the data network to a fluid network, you see that it's very intuitive how you derive the throughput from one end to another end. And those scenarios are very straightforward, just two links. Let's consider a case that's a little bit more like the internet, okay? Deriving the throughput for an internet-like scenario. So you see here, we have servers and clients, okay? Data will be going from the servers down to the clients through the backbone, the internet backbone. So for each connection end-to-end, we'll be going through how many links? 1, 2, and 3. So we'll be taking the bottleneck link bandwidth as the throughput. So we'll be trying to get the minimum of the 3 segments. Okay, RC is this guy, RS is this guy, clear. The middle segment, well, if there are 10 links in parallel, then this middle link here, capacity R, will need to be divided by 10, as I'm assuming the 10 connections are fairly sharing the entire capacity. So the throughput to be formulated is this minimum of RCRS and R over 10. In practice, however, okay, nowadays on the internet, usually it's either RS or RC being the bottleneck. You see, this is an end system, this is an end system. We subscribe access to the internet through some ISP. So this, usually the rate is low. Just like this, the application service provider, they are also subscribing to their ISP. This is also low. As opposed to the big R here in the middle of the internet, in the backbone, those are usually large. It's just that nowadays, there are a lot more connections sharing the big R. Okay? Most of the time, RC, RS are the bottlenecks. But occasionally, you might also see when network is really congested, R is not quite enough to allow all the connections demanding services. So you see, to determine the throughput for paths, usually you look into the bottleneck, okay, the thinnest pipe in the whole way, right? So there was a question from Justin. How does the sender know that the packet was lost? Does the receiver send a message to tell the sender? You know what, that's usually the way it works. But in order for the receiver to detect that there's a message loss, there needs to be something in the packets coming in sequence. For example, a sequence number there. So when receiver sees a gap in the sequence number, then the receiver can send a message back to the sender, hey, there's a gap. Resend that particular packet in that sequence number. Okay, so you will see TCP, a transport layer mechanism that handles packet loss, is doing it this way. All right, good. And you know what? We move on to the next topic in chapter 1. Okay. This is actually, there's nothing technical in this this particular chapter, in chapter 1. This is 1.5, by the way. What we want to do in this chapter 1.5 is to explain why layering. So this video explains why. And the short answer is because the network is complex. And we need to come up with a way to store things. Now, let's recall all the terms we've referred to since the beginning. Right? We've seen hosts and systems. They're essentially the machines composing the edge of the internet. And then the core of the internet, right? The other one at the center of the internet being a mesh of interconnected routers. And then connecting the edge and the core, we do have these access networks or access links that operates different kinds of physical media running different kinds of modulation mechanisms. Yeah, access network. So these nuts and bolts compose and form the physical infrastructure of the internet. So this is more the hardware side of the internet. But we also talk about that, hey, hardware is not the only thing that makes the internet work magic today. A lot of times we rely on these applications in order to what? To see a page that we are looking information from. Okay, so applications such as World Wide Web email. And these applications, a lot of times, right, it's implemented in a way that there's some part of the application running on one physical entity and then another part running on another physical entity. So if you recall for World Wide Web, there's the client side on the client machine, and then there's the server, the web server running on the web server machine. Okay? And these are client and server side will need to communicate based on a specific rule. Okay? And so those rule forms a protocol. So there's also a protocol for the World Wide Web. Okay? So this is one example of the software on the internet. And there are a lot of these softwares. Okay? And application is just one kind of software, right? So in terms of software, okay, there are a lot more to talk about, a lot more pieces. In fact, the hardware part, and this is a very simplified view, okay, there are also a lot of other hardware pieces as well. Okay. In fact, to talk about a complex system like this, we do have a major question to begin with. Okay. Is there a way, a hope to organize these pieces so that it's a little bit easier to teach or a little bit easier to discuss? Okay, not just between the senior network engineers, but also for the incoming network engineers, and how the senior ones teach the junior ones. Okay. Yeah, so that's why the textbook is organized also. Application layer, transport layer, network layers. So it's a complex system, okay, as a short answer. But now, longer answer. And Polly found that sort of complex notion or abstract notions are easier explained if I draw analogy, okay, from things that you are familiar with. Okay, so this next video is a little bit long, 6.5 minutes. Let Polly draw example from air travel. Okay, you'll see in this video that the air travel, there are also layers of mechanisms. Okay. Let me try to use an analogy, air travel here, to show you that it's kind of important to have some sort of organization, some sort of architecture, okay, to make sure a complex system will work seamlessly. And you will see also air travel and internet. Okay. Air travel to communicate people, internet to communicate data. They're somewhat similar, and therefore the architecture used by air travel is similar to the architecture used by the internet. Yeah, by architecture here I meant the service model, the way the service operates. Now, recall your experience traveling through air. First thing you do, purchase the ticket that guarantees you a seat. At the day of travel, you walk up to the counter, you present your passport and the ticket number. They will allow you to check in your bag and give you the boarding pass. With that, you go to the gate and they let you into the plane. And then the pilot will be negotiating with the traffic control of the departure airport and decide which runway and at what time the plane can take off. And then for a long time, you're just sitting in the cabin and try to get some sleep. But the pilot is busy doing this, okay, routing the airplane. Okay, so as the plane crossing border of some air control, communications will go on again and making sure that the planes traveling the air, the space, will not collide to each other. And hopefully everything is fine at the arriving airport. Again, pilot talks to the traffic control and find out the runway and the time to land. When the gate is connected and open, we may now leave the plane. Most of us go to the baggage claim to pick up our bag and exit the airport. So it looks like it's a series of steps. Very simple. But if you think about it a little bit more, right? Purchasing the ticket is important so that it guarantees you a ticket. So that when you go to the counter, when you're trying to check in your bag, they recognize you, right? And the base of the recognition is on the ticket number, okay? Acquired here and checked here. And in return, you get a bag number, which is used again here. You get also a C number, which is used again here. So there are still some communication that needs to be done, for example, between the steps, in between these two steps. Okay. So this component here, more closely related to this component. This component here is also more closely related to this component. And this component also connected and related to this component, even though this is at the departure airport and this is at the arrival airport. Okay. So you see that there are components that are related and there are some base in order to communicate between the staff members here and the staff members here. Okay, the mechanism here and the mechanism here. But you see also, for example, baggage check here, well, it has less to do with the pilot communicating with the central control. Okay, you see also a little bit, right? This is a little bit more like the internet core. The functionality is quite different. But these are a little bit more like the edge of the internet, where you're trying to track data. Here we're trying to track passengers and the belonging of the passengers. Okay. And so that it's probably not that hard to see. There's a architecture there, okay, and it's kind of laid out in layers like this, right? This is communication to traffic control, but at the end, communication to air travel on the other end. Communication of air travel, but from region to region to region to another region's traffic control office. Okay, so to regional office, it's just to make sure that the height and the orientation of the travel is correct. Now these involves also runway. So you see there's slight differences between these two layers. Now these three are more handling the passengers and baggages, not handling the plane per se. Okay, so which gate we get in and which gate we're coming out. So your families and members will know where to go to pick you up, for example, to welcome you back, for example. And baggage here, the number is important. At the destination, you also want to know which station is for the baggage claim. There are usually multiple of them, right? So it's also based on the plane number, the flight number. Similarly, ticketing. Sometimes you need to delay travel, right? So you need to call the ticket office again to try to change the day or change the class, okay? And the reference is always, for example, the ticket number. So for communication, you need certain important IDs, important information there, okay, to communicate within a layer. Okay, the claim ticket there for the bag is so that you can pick things up on the other end. But there are also certain numbers. For example, ticket number connects to a bag number. Ticket number also connect to a C number here. Okay, so certain pieces of information might be added there, either to allow communication within the same layer from local side to remote side, or information to allow components across layers on one side to try to relate to each other. Okay, yeah, so you see, air travel, okay, is a complex system. If any step goes wrong, it could end up being a disaster. Okay, needs to be well structured to make sure also that it's efficient. So there are layers. Okay, each layer implements a particular function. Okay, a particular subservice. Okay, and so there will be some internal actions, but they will also depend on services or functions provided by the neighboring layers. Okay, from the layers below. Okay, or they might also need to provide supports to layers above. Yeah, so that's the long answer. And you might find similar layering structure organizing transport systems, okay? Not just the passengers, not just data, but maybe cars, other type of things that we transport. All right, so this last video explaining why layering is just to emphasize the benefits of doing it, layering. First, you heard, easier to explain. Second, don't be surprised, it's easier to maintain a complex system this way, and it's also easier to upgrade, advance a system this way. Hopefully with the air travel example you see, in large complex systems, where we have lots of these pieces, it's really good to have some explicit structure so that it's a little bit easier to identify, in case there's a bug, which piece the bug is, and to find out what are the related pieces might be partly to blame as well. So having explicit structure, really good. And you see in the air travel example, we have this layered architecture, layered service model. That's exactly what we're using, okay, to manage, to organize internet's operation. And we call that layered service model also the reference model, because we are referring to these pieces on the internet in layers as well. Okay, so it's our reference model for discussion among the network engineers, okay, which you are becoming one as well. All right. So this way of trying to break a large complex systems into pieces, okay, and to define, okay, the functionality of each piece is also called the modularization. All right, so after defining the functionality of each pieces, after finding out the relationship between the pieces, okay, we implement the individual modules functionality. We also implement the interfaces to communicate from module to module. Okay, so that is called modularization. Okay, this is really common. We see in large software systems. Okay, because it's a lot easier to maintain. It's a lot easier to debug problems. And it's also a lot easier to improve the system, to move a complex system forward. Okay, because you see, the important functionalities are well modularized. So if we need to change the way we implement the functionality, we can just change it. Okay, and that change does not need to propagate through the entire system across the different modules. Okay, so a change, okay, in a layers service, a change within a piece, a change within a module, okay, can be transparent to the other modules, okay, because the APIs are already well defined. There's minimum communications required. All right, so it's just like this. Here's an example. If we change the gating procedure and we decided that we let the first class passengers to go last, hey, it's not going to change how the pilots communicate with the traffic control, right, in order to find out which runway to take off. So each module more or less independent, and the communication across modules, across layers are minimal. Modularization, or layered reference model, layered service model. Sounds nice. Can you think of anything that suggests such a layering is not exactly good? All right, I'll let you ponder, right? Such a layering structure Can there be disadvantages of doing it this way? Right? And we move on to the very last set of videos for chapter 1. Hey! So this first video, I will finally introduce and overview the Internet Protocol stacks, or better known as the TCP/IP stack. Here's the Internet Protocol stack, and you see here what I'm illustrating. It's in the layered architecture. The layer at the top is the application layer. So these protocols at the application layers are, literally to support the applications. For example, HTTP is supporting the web application. So you do have application processes sitting on the browser side and another application layer process at the web server side. And there's a protocol there. For example, a message go out is necessary from the client to request for a web page, right? And that web page will be another message coming back the other way. Well, that's pretty much what HTTP defines, right? So these messages to control when to start sending and which web pages to send. Transport layer, that's one layer down. The functionality is essentially to allow these application layer protocols to specify, whether these data that I'll be sending through, these data packets I'll be sending through the internet is going to be reliably transferred or best effort transferred. So this is to administer data transfer from client to server process or vice versa. Network layer protocols, on the other hand, very special. All these packets, oh, by the way, packets, when it arrive at the network layer, it's called another name, datagram. So these packets coming from the source, right, needs to find a way to the destination. You see, at the core of the internet, we do have a mesh of interconnected routers, don't we? A router could have multiple connections to other routers. So each router will need to know, which is the right router to forward next so that the packet will arrive at the destination with the shortest distance possible, right? Because you do want the packets to arrive at the destination as soon as possible. So a good routing protocol is to ensure something like this. So network layer, the protocols there are essentially to handle packets being forwarded and the directions of how these packets being forwarded in the core. Link layer protocol. So these are very special. They work a little bit like, honestly speaking, the transport layer protocols. Transport layer is to handle data transfer from one process to another. Link layer protocol here also handle data transfer, but it's between one network element to another one network element, one network hardware to another network hardware, or a network entity to another. For example, between two routers directly adjacent to each other, there's just one link. So this might across several hops at the transport layer, but link layer protocol only handles data transfer in one hop. So it deals with the data transfer very locally within a link. For example, Ethernet is a link layer technology, a link layer protocol. All right, so the closing of the video is a little bit abrupt, but we don't talk about the physical layer. It's definitely beyond computer networks. It's a harder part, of the whole communication system. Now, the very last video, Polly nicknamed the video "A Day in Life of a Data Packet," on the internet. So you will see in this video how a packet travel down these layers to the bottom of the sending end system, and how that packet go out and travel from router to router and eventually reaching the destination end system, and then get sent back up one layer at a time to the receiving application or the receiving process. 6 minutes, a little bit long, but it should give you a good sense. We talked about protocols sorted in layer, and we talk about the hardware side of the internet having these nuts and bolts connected. You will see both of these notions in one video. With the layered architecture explained, what I'm showing here is the software side of the internet side by side with the hardware of the internet. So where are the hardware in this example? Look, Look, here, and here, and here. So these are end systems. Okay, this one is the source, and this one is the destination. You see that at the end systems, the entire Internet protocol stack is implemented and running. Similarly for the other end system. But in the core of the Internet, you see the router over here. And this is a very special entity, hardware entity. It's called switch. But to be precise, this is the link layer switch. Its functionality is limited. Okay? Unlike router, this is a network layer device that implements the protocol stack from the lowest up to the network layer. The link layer switch is a more limited device. It implements only from the physical to the link layer. Well, then you see how it gets the name. It's a link layer switch. And if you want to be precise, you can also call these routers the network layer routers. Or sometimes we actually call these routers network layer switches. Okay, so both of these entities are doing switching, but doing the switching at a slightly different level. All right, now walk with me and let's see how the data gets passed down the protocol stack, out of a physical entity, and through the network, reaching the destination. The first step is this. Yeah, one particular user typing things up. So at the application layer, this component generates a message. Yeah, a packet at the application layer is referred to as a message. The application layer component will pass the message down. As the message arrives at the transport layer, a header is being appended in front of the message. Okay, because it's appending, therefore these additional pieces of information is referred to as the header. H stands for header. And this is a header appended by the transport layer, therefore HT. The whole thing together, this packet, is referred to as the segment. So a packet at the transport layer is called a segment. And you see that this header here is very important. This is to allow the transport layer component at the source side to communicate with the transport layer component at the destination side. Okay, so this is a little bit like at the airport. When we're checking our bag, the counter is going to give us back what? The passport, the e-ticket, and what? The baggage claim ticket. Okay, so that baggage claim ticket, that additional information, okay, in order for you to find your bag, is a little bit like the headers. Okay. And now the segment is going to be passed further down to the network layer. And guess what? The network layer component is going to append some more information to it. And that is in the header as well. But this is the header for the network layer, HN. And the whole thing now, the packet here at the network layer is called a datagram. And the whole datagram is going to be passed down further to the link layer. And guess what? The link layer header is going to be appended, and we call a packet at the link layer a frame. So this frame here, now arriving at the physical layer, what physical layer is doing is simply modulating the 0 and 1 bits, okay, onto the physical media. So it's going to go out shortly through the network interface and arriving at the router here. Now I'm skipping the switch here because it's a link layer device. We'll not be able to cover the link layer chapter. So this message is going to arrive here at the router, receive at this physical layer, and the signals gets converted to the digital form. So we restore the original frame back, and that's passed up into the link layer. The link layer at the router is going to examine this header and see if there's any additional function that it needs to perform. When everything is done, guess what? Okay, this header is going to be removed. So only the message with the transport layer header and the network layer header will be passed up to the network layer. You see here, the message is being passed upwards, okay? Because the network layer component of the router still needs to check this, okay, and see if there's something that the network component needs to do at the router. So this is going to be examined, okay, and functionality is performed. Now this part, hey, as this is a router, there's no other layers above. So this is going to be copied over, okay, and stand by there at the outgoing interface. Now before that message go down to the lower layer, the new network layer header is appended. And this one is a datagram. It gets passed down to the link layer header appended. And this is a frame. It goes to the physical layer, bits modulated, traveling the link and reaching the destination. Similarly, the physical layer is going to recover the 0 and bits and give this up to the link layer. This checked by the link layer, and the remaining gets passed up to the network layer. And you see this removed, this part gets passed up to the transport layer. This removed, and this part here gets passed up to the application layer. And here, the destinations processed there at the application layer finally see the message coming from the source originally. So this is how a message travels through the protocol stack and the physical infrastructure and more protocol stack up and down until all the way up to the application layer at the destination. All right, so that was chapter 1. And we'll start chapter 2 by talking about the network applications. So this video is to inventory all kinds of network applications we've been using. And you know what? Quiz 7 is going to follow this video immediately. To make sure that we're in sync, let's inventory some of the popular network applications here. Email, web, nothing more need to be said. They are obviously email and web. Text messaging, Line, WhatsApp, what else? A Google Messenger. And if you guys are watching this from a YouTube live stream, that chat room is a text messaging app. Remote logging. If you downloaded a client to remote logging to the PA server, then you're using a remote logging application or remote logging service. P2P file sharing, the most well-known one, BitTorrent. Okay. Multi-user network games. Okay, so this is a more formal way of calling online games. Okay, so some of these online games are running on desktops, going to the game server somewhere provided by the game company. The client can be nowadays running on smartphones. In fact, probably more games people are playing are mobile games. Okay, so the client is on the mobile platform. And then the multimedia applications. Here we have the streaming stored video, and we have the real-time voice. So this is also called the voice over IP. And we have the real-time video. Okay, well, real-time video conferencing, of course, also comes with audio. Okay, so essentially these three are multimedia applications. The difference between this and these other two is that the video is actually a playback video. So the video is already stored in one of the video content server, and when you request it, it is just playing back the video. But for these are the live video being generated as you guys are having conversation, as we are having conversations. So the delay requirement for live audio video is a little bit higher, more stringent. So what do we have as real-time video conferencing apps? Google Me, the one we have standing by here, allowing you guys to call in, is a real-time video conferencing app. So there are other real-time video conferencing apps such as Zoom, Microsoft Teams. What else? Well, Skype. Although transfer audio, it also transfer video. So Skype is also a real-time video conferencing app. So there are many options here. Social networking. Hey, Facebook, IG. One can probably come up with others such as Snapchat. So there are just increasingly more of these social networking apps. Search, Google Search or Bing. Yeah, each of these is also an application or a network service. Cloud computing, Amazon AWS, for example, is a cloud service. All right, so quiz 7. Yeah, so this quiz is a little bit special. Polly will survey young people so that she will not be so out of sync of the society. Okay, and what's being nice about teaching in college is exactly this. I have access to you guys, okay, young people. So quiz 7, let me ask you. For the first part, tell me the top 2 network applications you use on a PC or laptop, okay, when you are stationary. and tell me the 2 network apps you use when you are mobile using the smartphones. And then the 2 games you play regardless of the platforms. Okay, so this can be, of course, the game consoles as well. All right, good. And this is a straightforward quiz, so I don't expect that you need a lot of time. So let's now move to, I think, week 3, quiz 7, right here. Okay, let's move to week 3, quiz 7. Okay, you guys have 2 minutes to think about it and 1 minute. 1 minute to type the answer up. And by the way, in case you have multiple members and all of you want to say something, what you can do is have the rep type up the rep's answer and you reply to that post. All right, good. And that's start counting time, 2 minutes. Hey, faster posters gets bonus. Okay, we have a winner. All right, first. Yeah, so this is Zach's often used apps. So maybe Anthony and Vincent. Yeah, you guys have you guys use different apps, maybe. Yeah. So feel free to reply to Zach's post there if you want to let me know. Oh my God, the score is dominating. All right. Team 12. Interesting. Okay, that's about the time. Let's see, team 1. On PC, Discord and Reddit. Okay. I used to spend a lot of time on Reddit, but not that much time anymore. IG and Reddit. Oh, okay, Zach. LOL. Okay, Honkai Star Rail. Interesting. I wonder what that game is. Hey, you know what? I'm gonna look it up. And team 2, Sylvain. Discord Messenger. Yeah, so I see, yes, Discord and Messengers are somewhat social network / messaging apps, right? Horizon Zero Dawn. LOL. Okay, so LOL remain popular over the year. Horizon, is that a PS5 game? Messenger, Google. Facebook Messenger. LOL again. Anthony, I know you guys have something to say. Discord and YouTube. I do spend a lot of time on YouTube these days. Reddit and WhatsApp. Yeah. So in Taiwan, we use Line more. But I'm trying to cut all these messaging platforms because they have become disturbing. For you guys, it's probably not, but in my case. Civilization, interesting. Okay, this seems to be the building type of games. Okay, interesting. I can see, Anthony, you and Zach, although from the same university lifestyle, very different. Tao here, Discord and Google. The score WhatsApp. Hey. LOL. Wow, it's still popular. I see. Minecraft. Of course. Spotify? Yeah. Yeah. Hey, part of the reason Polly is on YouTube a lot is music. So some of you stick to Spotify. I think it's lower cost, right? The score? LinkedIn. All right. Okay. But this is more professional. So Justin, ready for jobs, I guess. IG, YouTube, good for you. Sweeper, okay, I enjoy this tiny little game. Yeah. Rainbow. Google related, sure. Gmail, I see. Facebook. IG and Messenger when you're on the run, sure. MLB, 9 innings. Okay, so this is probably a PS game or Xbox game. Angry Bird. Okay, so this is a smartphone game then. Slack and Netflix. Interesting. Okay. Podcast Addict. Okay. Okay. Yeah, when I'm driving, yes, podcast, of course. LOL. Very interesting. But I see similarities, right? Video apps, music apps, and social apps, IG, Facebook, and messaging apps. Games, however, I see a lot of variety. Yeah. And some of you like turn-based games, some of you like, story games, and some of you like more intensive battle games, strategic battles. All right, thank you for all the input. And you know what? It's 11:12. It's time to take a break. We'll resume lecture and continue to talk about applications. And we'll start by talking about if you now begin to think like a network app developer. Okay, how does one develop a network app? So that's coming up. If you want to develop an app of your own. So 10 minutes. Start counting 11:12. We resume at 11:22. All right. Okay, so it's not quite yet 22, but yeah, I looked up the guys you guys play. Very interesting. So I think this is from Team 1, the Honkai. Yeah, amazing graphics I can see. It looks very addictive. Okay, it's a PlayStation game. And I guess there's also a PC version of it. Amazing graphics. It looks like a storyline game. Yeah, there's probably a long story behind it. Yeah. Okay, sounds like good life you guys have there. All right, so hey, how about we go back, come back, okay, to computer networks and do some learning, okay, and have fun in the meantime, hopefully. Yeah, so network applications. You see that we're using them all the time. Very useful. Okay, I guess part of the reasons that you guys are taking networking courses, of course, you see, it could be right on your career objective. Okay, so now start thinking like a developer of a network application. All right. This video, relatively short, is to give you an idea what a network application developers do. So essentially, write the network programs. Now, to support all these applications, the principle is quite straightforward. Essentially, we write programs. There involves at least two parties. One program sits on one of the parties. Particularly, each of the programs sits on each of the end systems involving the communication. Okay, so they will be communicating, sending messages over the internet. So for example, web server program sits on the web server machine. Browser sits on the client machine. And these two programs send messages to each other. Much like this. So we might have a web client here. We might have another web client here. And the web server is down here. And we establish connections like this. So this client's program interact with the server's server program. This client's program interact with the program running on the server as well. Okay, so you see that the server program here needs to be a little bit more powerful, allowing requests from these clients, okay, frequently and potentially simultaneously. So essentially, in order to create these network applications, we design how the messages are exchanged, meaning designing an application layer protocol. Afterwards, we program the softwares. There'll be one part running on one end, the other part running on the other end. So this example here is a client-server application. For P2P, one runs on peer, the other runs on another peer. But in P2P, these two programs usually are identical because they are both peers. Now, what's unique here is this. Applications run only on the end systems. In the network core, these routers, the routers do not run anything particular for a particular application. Okay, so the core devices do not run applications. They do not run specific functions to support individual application. Okay, so applications are strictly on the end systems. So clients, limited devices such as a smartphone, such as a laptop or desktop, are on the edge of the internet. But you see here, servers, more powerful machines, they can be quite expensive. Some of them can be just as expensive as the routers. But these servers are also at the edge of the internet. They are also end systems. Just don't be confused. Okay, so these end systems, there are programs running and exchanging data such that we can perform specific application or specific service. All right, so essentially you write these network programs. So one for the server, one for the client, for example, and have these two programs sending messages to each other. Okay, for example, for a game, you have game client and you have server there maintained by the game company, and there's a program running there. There's a program that you set up locally, and then these two programs are sending messages to each other. Okay, so the essence is that you have two processes sending messages to each other in the simplest form of network applications. Okay, but writing code or creating these programs is just what the end products are. But when you are designing a game, when you are designing a network service in general, you still want to think about, right? In the game's case, you have game server and game client. It's again a client-server based communication, right? But sometimes I see Miguel is asking, in peer-to-peer, do we need to write server and client separately? Okay, and server and client in the same program. In P2P, each of these end systems might be serving, might be requesting for services. You are right, Miguel. For peer-to-peer network applications, that program that you run on each of these peers will need to have the server function, will need to have the client functions. Yeah, and it's in the same app. Okay. And you know what? Hey, for a service that you hope to develop, would you like it to run in P2P model or in the client-server model? And is it going to be just one server, or are there going to be multiple servers so that your service can scale to many, many clients? Are these servers going to be somehow organizing a certain hierarchy, so that there's a good property in balancing the load? So this next video talks about, before you can write the program, you want to think about, hey, what are the end systems involved? Okay, and how are you going to connect these systems? So the architecture and the communication model among these entities. Okay. The first thing we decide designing an application is its structure. There are two major models, client-server and P2P. The third kind here is the hybrid of the two. This is usually for bigger services where part of the service fits better running in client-server model and the other part running in P2P. The client-server model is straightforward. There are two ends. One is server, the other end, the client. The server is one of these powerful machines that's always on, running on permanent IP address so that they are always reachable. Now, given the scale of the internet service today, instead of using just one physical server, we need multiple of these, and they are housed in one of these data centers, so that we could serve thousands and perhaps millions of requests at the same time. The clients are you and me. We are lower-end machines and scattered around on the internet, communicating with the servers, requesting services from the servers. Now, unlike the server that are permanently connected, permanently reachable, we're moving around, okay, only intermittently connected. This is because as we move, we might be assigned dynamically a new IP address. So our IP addresses are not permanent. So using one IP might not reach us at another time. So that's why we don't see clients directly communicating with each other. And we see two examples on the left here. So someone in the car might be trying to find the driving direction, so that could be a request to Google Maps server and getting the direction back. Now this could be a student trying to look up PA assignment, so a web request to the web server and the web page or the PDF file returning to the client. In the P2P model, we no longer have the always-on servers. In fact, all these end systems would directly communicate with each other and treat each other equally. So in this P2P world, think of it this way. Everyone is born equal. So the equal peers will request services from each other. They also provide services to each other. So such a characteristic is called self-scalability, because as we join such a P2P service, we ask for services, but we also open up our resources and adding new service capacity. Now, the only drawback of P2P is this. Hey, the peers, they are all intermittently connected, running on dynamic IP addresses. How do we ensure a P2P services is going to stay connected all the time? Yeah, the management of these peers is the complex part. The third model is using a combination of the former two. This is usually used by bigger services where there are service components, and some component better run on client server and the other components P2P. Now, Skype is one such service. The component in Skype that's tracking your contacts and where their current IP addresses are is in client server mode. That's called the directory service. Okay, so the central directory server allows you to find the IP addresses of a remote contact. Once you decide to call someone, the calling service runs in P2P mode. That IP address is used by you to make the P2P direct call. Yeah, okay. Yeah, so I was trying to type up something in response to Zhen Yu's question. Okay. You know what? The clients, it's not like they want to use dynamic IP address. It's more nowadays how we get connected to the internet. You see that when you are holding a smartphone, as you are walking around, at one point you might be connected to a particular network, and that network offers you a particular IP address so that you can be connected to the internet. But as you move out of that network, another IP address might be assigned. Okay, just like if you move from the EE building to the CSIE building, the IP addresses you get from accessing the Wi-Fi's might be different. Because IP addresses are assigned such that the computers nearby will share the same IP prefix, the first few bits of the IP address. And as you move geographically to a different location, then you get a different IP address. Okay, it's just how we manage the IP address on the internet. Okay, so it's not like the client wants to change. It's just that we go places. Okay, servers, then you imagine, right? They are somewhere fixed. Okay, I hope that clarify how come the clients are using the dynamic IP addresses. All right, good. And hey, after you architected your app, right, you want to start writing. This is the thing you need to create, a socket. Okay, this video is a bit long, 6 minutes, but this is for many of you, this is a new notion, but this is necessary for any network programmers. In fact, for PA 3 and 4, and 5 and 6 and 7, 8, 9. All right, so pay attention. And by the way, turn your volume down a little because this next video, you might also hear a little popping sound coming from Polly. Sorry about that. I was too close to the mic. To implement a network application, it's equivalent of allowing process-to-process communication. Okay, so in client-server's case, a client process communicating with the server process. In the P2P case, peer-peer processes communicating with each other. Now, take note, the server process, remember server is the one that's always on, right? So server process is always started early, since the beginning of the service. Only when the service is started, then you call that the service is available, okay? And it's always there waiting to be contacted. The client process is the one after being started by the user, initiating communication to the server and getting something back from the server in return. Now in P2P paradigm, the exchange between the peer processes are then a little bit complex. Each peer process will have the client side and the server side implemented. Okay, the difference is that this peer process client side contacts the server side of the other peer and vice versa. But either case, process-to-process communication. This is how you enable network applications. Now, let's take a step back and review. What is a process? It's a program running on a machine. So in fact, for two processes on the machine, there are occasionally the need to communicate with each other. Okay, this is possible and enabled by this set of API called Inter-Process Communication API. This is defined by every operating systems today, and this should be covered in the operating system course. Now, in case you don't have this, you might want to look it up a little bit, IPC. Now, in this course, we talk about process communicating with another process that are on different hosts. So two processes exchanging messages on different machines. How do we do this? We do have another set of APIs defined called the socket API that allow us to do this. If you call the socket API, a socket is created and associated to a process. And that's when the process can begin sending, receiving messages through the internet. Now, think of a socket as if there's a door. On one end of the door, the sending process pushes messages out. The other end of the door, we have the transport infrastructure. So let me explain with the picture here. Sending process here. Sending process pushes the message down, reaching the transport infrastructure. So the infrastructure here will move the packet further through the internet and come to the receiving end of the infrastructure. From here, messages go through the receiving socket and reaching the receiving process. And you see, process-to-process communication enabled by the socket API. Now, let me draw your attention here. From this line and above, this is application layer. Everything running here needs to be controlled and defined by the application developer, application designer. So it includes the functionality of the sending receiving processes, as well as the kind of socket we want here and here. Hey, why is it challenging? Because the transport infrastructure, there are actually multiple types of services being provided. So in order to call the socket API creating a socket, one needs to know which transport protocol to choose. This depends very much on the kind of applications you're designing. You might also define additional parameters so that a process is correctly associated with the socket. One very important parameter to define before creating a socket is called the port number. So the port number, you can think of it as a unique identifier for a process running on a machine. So keep this in mind. And now let's take one step back and think about why we need a port number. All right. So let's see how we uniquely identify a process running on the internet. Well, first is, of course, try to find the machine the process is running on first. How do we identify a machine on the internet? Yeah, we do have IP address. You guys should all have heard about IP address. It's a 32-bit long number. With this IP address, we identify a machine. But the question here is, does the IP address allow us to identify a process running on the machine? Having just the IP address, is it sufficient already? I know what you're thinking. You're probably thinking, no, not quite. If there are multiple processes running on the machine, then you cannot see exactly which process, right, we're looking for with just the IP address. Therefore, in order to identify uniquely a process running on a machine, we need something extra, the port number. So for a process running on the internet, in order to uniquely identify it, we need the IP address plus the port number. Okay. So a few example port numbers. For example, HTTP server, this is to support World Wide Web. It typically runs on port 80. So the socket connecting to HTTP server is on port 80. For mail server, port 25. It's a very common practice on the internet. For these very well-known services, we use a fixed port number so that it's easier for the programmers to remember. So that is also saying to send a web request, which is a HTTP request, to a server, gaia.cs.umass.edu. We send that message to here, or that socket is defined by this IP address and this port number. So this is the IP address of the web server, and this is the port number of the server process running there. All right, so socket sounds easy. Okay, when you create a socket, you need to specify the type of the transport infrastructure, transport layer service you want to use, and a few parameters in addition. And one important one is port number. So we talked about port number, but we have not yet talked about the transport layer service. We'll talk about that in the topic 9 and 10. Okay, and let's skip to the next thing, messaging. Okay, the messages. Now we have socket created connecting processes, we can begin to send messages. But you see, what we're talking about here is general application design. So an application can be a little bit complicated. The server could be providing multiple services. So how do we know, right, when the server receiving a message, the client is asking for service 1 or service 2 or service K? And vice versa. The server could be sending a message back to the client. And how does the client know what is the intention of the server? The message is being exchanged between these two processes, need to be clearly defined. So that includes the type of messages. So one may be sending a message for a certain occasion. So there could be multiple types of messages defined for an application. Now use World Wide Web as an example. The client typically sends web requests and the server sends web response. And inside the response that contain the web page the client is asking for. Now, continue to use the World Wide Web as example. Inside a web request, there'll be some fields, okay, we define. For example, time of the request, browser of the request, or language preferred by the user sending the request. Okay, so there'll be fields like this with the values that will contain in the web request arriving at the server. Server knowing the syntax, okay, of the request message will understand exactly what's going on the client side, and therefore send the most up-to-date web page in the preferred language, for example. Now, we also define semantics of messages because, again, using World Wide Web as example, the web response a lot of times sends back, for example, status. Okay, so this is the status of the request. Now, if the client is looking for an object that's no longer existing on the server, you see very often a response coming back saying 404. Yeah, what that meant is object not found. The web page is not found. So 404, that status comes with a meaning. Okay, so we define also the semantic of some of these code words. Now, this is really nice to send code words because you use few number of bits instead of sending longer English strings. Okay, so meaning of the information in the fields. Now, of course, right, this is almost like defining a language. Yeah, the rules, the timing we send the message, and when we receive a message, what kind of message we generate next. Okay, so all four together, the types, the syntax, the semantics, and the rules of corresponding back and forth between the processes. That's called the application layer protocol. So each application defines its own application layer protocol, defining the messages it requires and the syntax, semantics, and the rules of exchanging the messages. Now, many of these application layer protocols are open, meaning if you just Google, you identify, for example, the World Wide Web's application layer protocol. That is actually called HTTP, and it's defined in one of these RFC documents. So these protocols are open such that if I want to come up with my own browser, because I know, hey, HTTP requests what the format should be like, the syntax, semantics, and rules, then I can write a browser such that it behaves just like the other browsers following the same RFC document. Same for email. Okay, so these open protocols are nice out there because each one of us can develop independently a new web browser, a new email reader, a new web server, a new email server. Now, many of the applications are commercial, owned by companies. So they do have their protocols, but they are not open. So these are the proprietary protocols. For example, Skype, we talked about using the hybrid model to communicate. It's got its own set of messages and syntax and semantics, but they're closed. It's hard to come up with our own client, a Skype client, such that it works with the legit Skype clients. Okay, so when you define a protocol, you find what is the best architecture, how the components involving the whole system communicate. You try to create sockets, and you define the messages, okay, what they mean and how they are exchanged. All right. Now, topic 9 and 10, this is to come back to address that slight open issue there when we are creating socket. What transport layer service we use? It actually depends on this thing, QoS. Quality of service you would like your user to experience. Okay, I mean, we would hopefully that the users will be happy with our service, right? That way they would recommend the service to others, and then you have a bigger customer base and you get more profit. Okay, so you need to know better what quality of service you are looking for, designing your application as well. And there are 4 of these commonly used QoS. Okay? And they actually correspond very well to the 3 performance metrics we've already talked about: delay, loss, and throughput. But there's a 4th one. Guess what it is? Now, in order to know what is the right transport layer service for an application, we need to think a little bit more about the application we're designing. what is the nature of the content we're sending, and what the users might be expecting. The first criteria is called the data integrity. This concerns whether the data needs to arrive without any loss. The key word here is that if the apps are about sending text-based content, for example, a file, for example, a web page, for example, a text message, then users are expecting 100% reliability. If we're sending audio video, it's okay to have some loss. Think about speaking a sentence. If we miss a syllabus here or there, the listeners being human beings, we're intelligent. We can still make up the full sentences or make up for what the speakers want to say by looking at the context before and after the sentence. Second criteria, growingly important, timing. This is especially the case for interactive applications. So the key word here is interactive. Internet calls, live video sessions, or shooting games, interactive games. Users are indeed expecting low delay. Okay, and you guys know. Third is throughput. Okay, this is sometimes referred to as bandwidth requirement. Nowadays, we send multimedia content, audio, video. Text-based content, it does not require too many bits to send them, so it's not an issue. But for video and audio, we do need a substantial amount of bits per second in order to deliver them, so that the bits after recovery, okay, is in good quality. So if you compare video versus audio, the throughput requirement for video is higher and audio lower. Text, much lower. So we need to somehow guarantee a minimum amount of bandwidth in order for these audio-video communication to be effective. Text-based applications are elastic apps because there's no strict bandwidth requirement. The requirement is elastic. Fourth criteria, security. This is probably nowadays the most important criteria. Are the users expecting we are sending data such that we are protecting their privacy? Okay. So these four criteria together, we actually give it a special term. They are also called the quality of service. So before we can define what transport layer protocol we use, we need to think through what kind of quality we will be providing the application service. All right, so 4 criteria. And the fourth one, I guess many of you probably guessed security. As Sylvain was pointing out, right? A potential benefit of having the clients using dynamic IP address is security. Yeah. If the IP address keep changing, then it's a little bit harder to pull these DDoS attack. And that's why DDoS attacks targets are servers. The machines are sharing the same IP address. And you'll be surprised, this is like DDoS attack or just DOS attack. It's happening on a regular basis, even as we speak. All right. Now, back to QoS. We're not yet done. Okay, you hear about the concepts. Okay, of course you will be thinking, I would like to have low delay. I would like to have no loss. I would like to have as much bandwidth as possible and everything secure. But you see, if you ask more, there's a overhead. There's a cost. Okay, for doing more. And not all of these internet services we see. Some are very popular. Okay. Ask all these quality of services. Okay, so guys, when you learn, definitely you want to hear about the theory or the fundamental concepts. But another way of learning that is very effective is to borrow, okay, from examples. So next, let's check out a few commonly used apps on the internet and what QoS they demand or they define. Let's go over a few common applications and see if we could sort out their quality of service requirements, or in short, QoS requirements. First application, file transfer. Transferring files are static objects, most of them text-based. Therefore, in terms of data integrity, we demand 100% reliability. File transfers, we do not expect they arrive in a few seconds. Okay, so it's not delay sensitive. As a result, there's no strict bandwidth requirement. Therefore, the throughput part of the QoS, elastic. You can probably imagine email and web objects. These are transferring also files, email files, transferring web pages. okay, web page files. Therefore, the QoS requirements very similar. The second application here is real-time audio video. So, first of all, the nature of content, audio video, different from text. Therefore, keyword, non-text, it can be delay tolerant. Okay. Another is it's real-time, that means it's interactive. That's another keyword, which means we do have delay requirement. And for real-time, that's showing the audio, video that's happening right now. So the delay needs to be less than hundreds of milliseconds. So you feel like it's happening right now. Audio, video, now there's time sensitivity. Therefore, we need to maintain minimum bandwidth. So there's a bandwidth requirement. And the requirement for audio, lower, video, higher. These days, some users might actually expect even higher bandwidth for video. Now, can you think and push a little bit and see if you know the QoS requirement for stored audio video? Well, first of all, keyword, audio, video, non-text. Therefore, you can probably guess data loss here is loss tolerant. What about the delay requirement for stored audio video? It should still be some requirement, but probably not as strict as the real-time audio video. And you're right. Delay can be a little bit longer. But given that there's delay requirement, the throughput is still hard. We still need to make sure that there's a minimum amount of bandwidth available. And audio video, the bandwidth requirements are because of the nature of the content. So it will be the same. Audio, 5 kilobits per second to a megabits per second. Video, 10 kilobits per second to 5 megabits per second. Now what about this one? Yeah, interactive. The keyword is similar to the real-time nature of this application, isn't it? Except that this is now game data. So you can imagine, delay requirement here, just as strict as real-time audio video. Is it loss tolerant? It's a little bit tricky, isn't it? What about throughput? If there's delay requirement, then there's usually a throughput requirement, but it should not be as high as video or even audio. So here, just a few kilobits per second. Game, this part is debatable. For some games, for example, shooting game, some of the players would argue, I want no packet loss. Okay. But for most of the interactive games, it's okay to have some loss. Okay. And then the users, the players, can try to repeat actions to make it up. What about text messaging? Keyword text, so no loss, obviously. Throughput? Yeah, it depends a little bit on the delay sensitivity, isn't it? And text messaging these days, yeah, it's also debatable whether it's time sensitive. Some will say yes, some will say no. Okay. But you see also that the delay we experience in text messaging, most of them are probably thinking delay, not network delay. Okay. Yeah, so you see, generally, text, elastic, not much throughput needs to be guaranteed. But text, usually people would like that there's no loss. But for audio, video, things get a little bit complicated. On one end, you want to guarantee certain throughput. On the other hand, hey, what about timing, right? Delay. Certain type of audio, video will have stricter timing requirement, but certain other type, less strict. Okay. All right, so now, given that you have identified the QoS for your application, now which transport layer service you choose? So this video overview the 2 transport services there are. In order to find out what is the right transport layer protocol for an application, we also need to know what the options are. We do have 2, TCP and UDP. TCP is the one more elaborated. UDP is very primitive. Let's focus on TCP here. The reason it's more elaborated is because it provides reliable transport. Think, a sending process and the receiving process. If we connect the 2 of them using a TCP at transport layer, data will always come to the receiver 100% correct. There's not going to be error. There's not going to be lost packets. How do we do that? Well, let's talk about that in Chapter 3. In fact, that's the main content in Chapter 3. For now, keep in mind, TCP provides reliable transport, no data loss. Second, TCP also does flow control between sending process and receiving process. The sending process here is checking whether the receiving process is busy or not. In case it's busy, the buffer gets full because data comes to the receiver and gets buffered temporarily here. If the receiving process is a little bit busy, the speed that we extract the data out to the application could be slow, so buffer builds up. If the sending process is sending data too fast, those data arriving to a full queue, full buffer, data get lost. If TCP is doing all it can to try to recover from loss, it doesn't make sense that sending process is sending data too fast to create data loss. So flow control can be some sort of communication going on between the receiving process and the sending process so that the sending process will slow down. Congestion control. It's a little bit similar to flow control, but it's between all these other routers in the middle of the path from the sending process to the receiving process. In case any of the buffers, in the middle on the internet is close to full, sending process slows down. If the buffer is no longer full, packets can go smoothly, speed also comes back up. So that is called congestion control in TCP. This, in fact, is also one of the main content that we'll talk about in chapter 3. So for now, just keep in mind, TCP does reliable transport, flow control, congestion control. TCP, however, does not do this. Timing guarantee, minimum throughput guarantee, security guarantee. So the other 3 QoS requirements we talked about, TCP does not provide. The only QoS guarantee it provides is reliable transport. So this is TCP. Now there's one more feature about TCP. It's called connection oriented. To set up a TCP connection at the transport layer, the sender and receiving process also do some sort of control message exchange to set up a connection. So this part of internet, although it's a packet switching network, but the behavior is a little bit like the circuit switch network. And there's a reason for it. This is so that we have more communication so we could recover from errors. UDP, it does not do reliable data transfer. There's nothing really going, no more communication between the sending process and the receiving process. Sending process is send, receiving process is receive. It does not provide flow control, congestion control, none of these timing, throughput, security guarantee either. There's no connection set up. So this is really the native packet switching network transport layer service model. Now you know, TCP essentially does nothing. You're right. The question is, why do we bother having UDP? Why don't we just use TCP? Yes, if you recall, among all these applications we've mentioned, text-based content, we prefer reliable transport. But is there other kind of content that reliability is not necessary? It's okay to have some loss. Yes. Sending audio video is not necessary to have 100% reliability. So quite a few of these audio video multimedia services, multimedia applications, prefer using UDP as the transport layer service. Yeah. So from that video you probably heard, right? For applications that does not require reliable transfer, UDP, because delay and throughput seems to be better if you send data through UDP. TCP is for the reliable service, so or services that require data reliability. All right, just like QoS, let's check out a few examples. For the popular services we see on the internet, which transport layer protocol they use, TCP or UDP? Here, let's go over some common applications and see what transport layer protocol they pick. Email, well, in fact, remote terminal access, remote logging, such as the terminal you're using to remote logging SSH to the PA server. Web downloads, file transfer, all these are what? Text-based, static objects. Reliability important, but it's elastic, no delay requirement. So not surprising, you see them all using TCP. So these are just the specific protocol, each of the application is using. Email is the application. The application layer protocol is called SMTP, Simple Mail Transport Protocol. For World Wide Web, this is the application. The protocol supporting World Wide Web is HTTP. File transfer, the protocol, FTP, standing for File Transfer Protocol. Now, these two other applications, streaming multimedia such as Netflix or YouTube Live, audio, video, reliability is no longer required. Therefore, you see, some streaming multimedia applications use UDP, but some stick to TCP. Internet telephony, Google Meet that we're using also on the side is one such internet telephony application. It's audio video as well. So UDP, and sometimes some of these internet call services are TCP. Yeah, and sorry to keep you waiting. Quiz A is here. Okay, so that's exercise. What we learned about QoS and transport layer services, TCP versus UDP. And C, okay, and C, how you would pick which of the protocol for a game that you're designing, okay? So should the game traffic be transmitted over TCP or UDP? Pick one you find fit and tell Polly why. And by the way, we have 3 games you want to consider. First one is Farmville. So it's a little bit like Animal Crossing, slow-paced. What you do is you plant the seed for a certain breed of flower and of rose, and you let it grow. Of course, you might also visit your friends' farm and appreciate their garden. Okay, so Farmville is something like that. And PUBG, it's a shooting game. Very intensive, very fast-paced, and it's life or death. And if you miss a shot, it could mean that you're dead the next microsecond. Okay. So would you use TCP or UDP for Farmville? Would you use TCP UDP for PUBG? And would you use TCP or UDP for RO? This is an online game, massive multiplayer online game. So what you're seeing in the screenshot is that, hey, many members of a guild are gathering and then chatting. Just talk, okay? Talk about school, talk about real life. In addition to the adventures they will embark right after the gathering, okay? So in a role-playing game, there are these, chatting setting, making friends, thing, and then there will be also, hey, as you embark on a quest, then you might run into big mobs, okay, and the team you need to work together. I guess timing there of a certain spell being casted upon a certain member or upon the mob can also be critical. So 3 games. What do you think for each of these 3 games, TCP or UDP, and why? And guys, this is an open-ended quiz. So yeah, so let's move to the score. It's on channel 3, W3 quiz 8. Okay, it's already 12:05. Okay, of course you guys can talk about it and see if you manage to come up with a solution for all 3 games and justify them today. Okay. If not, then there's a student asking what is PUBG. Hey guys, help me here. Okay, I know that many of you know what it is. Okay, it's a shooting game. So a bunch of the players will be taken, like Fortnite. But you probably need to explain Fortnite. Yeah, so a bunch of the players will be taken to an island, okay, an isolated island or isolated area, and you'll be dropped, okay, onto the island. And you'll need to kill each other until there's the last one standing. And on the island, you might be able to find these rifles or semi-automatic weapons and the armor. So yeah, you get to shoot each other. Sounds fun. Yeah, sounds fun. Okay, yeah, so hey, life or death. Good, so Guys, feel free to stay and think about it. But let me just say gently bye and play the goodbye music as you're working on it. All right? And hope you enjoyed today. You see that we end the lecture early because Polly is playing the video in a faster pace. If you find this okay, let me know. Just say okay while you say bye. All right? Okay, bye. See you next week. Okay, and by the way, quiz A here. Bye, thank you. Bye, thank you. Okay, bye, great. Thank you, Tao. So the speed is okay with you. Quiz A and quiz 6. So consider them take home. The due time is Saturday, 6 p.m. Okay, bye. Bye-bye. Yeah, I see Team 1 wants to finish quiz A here. Okay, good for you. Okay, bye. Okay, time to end the stream. Bye. Okay. Okay, thank you, Sophia. All right, now I know how to attribute the points from Zo Lambda to you. Thanks. Thanks. Okay, bye. Ending the stream.